Hello, I'm Zhang. I'm working with Hong Jin and Professor David Law. We're from Singapore Management University. In this work, we collaborate with Abhishek Sharma, Andrew Santosa, Asankaya Sharma, and Ming Jiang from Veracode. Now, I'm going to present our paper HERMES using commit issue linking to detect vulnerability fixing commit. The presentation will go through three sections in which first we answer the reason why we need to consider the problem of identifying vulnerability fixing commits, the motivation and challenge. Next, we will describe the design of HERMES and how we implement it. Finally, we will demonstrate our experiment results and the implications. Modern software projects rely on a large number of third-party libraries. Consequently, open source software users that depending on vulnerable third-party libraries, either directly or transitively, are under the risk of being attacked through vulnerability exploitations. Take the Log4Shell vulnerability as an example. It targets Log4j, one of the most popular Java libraries for logging messages and errors in Java ecosystem. By logging a URI that points to a potentially untrusted Java class, attackers trick the client applications into executing malicious code. As a result, a vast number of applications and cloud services that use Log4j, including Steam, Apple iCloud, and Minecraft, are affected. To avoid similar incidents, the open source software users must keep up to date with vulnerabilities. There are public vulnerability advisories such as the National Vulnerability Database or the Common Vulnerabilities and Exposures, where people can look up and monitor the vulnerability disclosure information. However, the process of vulnerability disclosure can vary from days to years. As an example, the CVE 2018-11766, which is a critical vulnerability of Project Apache Trust, was only disclosed 2 months after the vulnerability is fixed. As a result, the users of Apache Trust were exposed to the huge risks in these 2 months. Therefore, it is crucial to facilitate the awareness of vulnerability fixes as early as possible for open source software users. For example, as early at the time when the fix is pushed to the public source code repository. It is relevant to the problem of automatically identifying vulnerability fixing commits. Formally, the problem takes a commit at input and output the prediction whether the commit is a vulnerability fixing commit or not. Previous techniques have been proposed to solve this problem. They relied on commit messages or code change. However, there is another rich source of information which can be used. There are issues and discussion corresponding to this commit. They can provide us useful information such as stack traces, bug consequences, or even solutions for the vulnerabilities. Two examples for issue tracker are GitHub issues and Jira. See an example for a vulnerability fixing commit, which consists of commit message and commit code change. And we can see the purpose of the commit may not be readily apparent by analyzing the code change itself. Moreover, the commit message is uninformative, contain only 2 words. On the other hand, by considering issue that linked from the commit, it is immediately evident that the issue is related to a vulnerability. As we can see, the word vulnerability appears in the issue title. The issue description shows the consequence of the vulnerability, which is the SSE attack. Without obtaining the issue description based on the link from the commit message, a vulnerability fixing commit detector does not consider this rich and discriminative information. However, Studies have noted that developers may not always link their commits to issues. The proportion of unlinked commits have been reported from 35% to 40%. In the dataset of commits that we collected, we find that the problem is worse than what was reported in previous studies. Nearly 63% of commits are unlinked. For unlinked commits, HERMES use existing commit issue link recovery technique to infer links between each unlinked commit and an issue that best match it. At the high-level design, HERMES consists of 3 independent modules: an issue linker, 3 base classifier that are commit message classifier, code change classifier, and issue classifier. And the final one is a join classifier. As Daniel described, the message classifier takes commit message as input and output the probability that the commit is for vulnerability fixing or not. The patch classifier had the same functionality but receives commit patch or commit code change as input. For issue classifier, there are 2 cases that can happen. If the commit message references any issues on GitHub or Jira issue tracker, HERMES directly follow the links and use the content of issues as input for issue classifier. If the commit message does not have any explicit link to any issue, we infer a link to a single most relevant issue from our issue corpus using a commit issue link recovery technique. The content of the linked issue is used as input for issue classifier. Finally, the results from all 3 base classifiers are fused using stacking ensemble technique. Detailed speaking, for message classifier and patch classifier, we reuse the design from baseline model. In these 2 baseline, commit message and code change are treated as sequence of tokens. In detail, first, the raw documents are tokenized, normalized, and stamped. Non-alphanumeric characters are filtered to remove noises. We use a minimal TF-IDF threshold to remove infrequent token. Next, we transform each document into a vector of words count. The 2 sets of vectors are input to the corresponding classifier to train 2 support vector machine models. We use the 2 models to compute 2 probabilities that a commit is a vulnerability fixing commit or not, based on the commit message and the code change. For issue classifier, as mentioned, there are 2 cases that can happen with a commit that leads to 2 different flows of the issue classifier. If a commit had explicit links to issues in which the commit message references the ID of the issues, we first manually identify the relevant issue tracker corresponding to the project where the commit belongs to. Afterward, we use regular expressions which based on GitHub and Jira conventions for issue references to directly match issue with commit. For commits that have no link to any issue, we link each commit to the best match issue in our issue corpus of 290,000 issues collected from multiple projects in the dataset. Using our issue linker, we selected FR-link for each commit issue linking due to its simplicity and ease of implementation. In details of how the issue linker works, for each pair of the commit and issue, code feature and text feature are extracted from both commit and issue, in which code features refer to code terms such as method names, variable names. They're extracted following certain naming conventions, such as camel case qualifier name. Text feature refer to natural language terms extracted using NLP techniques. that are tokenization, word removal, and stemming. The similarity between the commit and the issue is calculated using cosine similarity based on the TF-IDF values of these terms. For each commit with no explicit link, we find the issue in our issue corpus that is the most similar to the commit and infer a link between them. At this point, every commit in our dataset either has explicit link to its issues or has a link to an issue in our issue corpus. Next, we retrieve the content for representing issue. For issue from GitHub, we obtain its title, body, and comments. For issue from Jira, we use its summary, description, and comments. If a commit link to multiple issues, we concatenate all the extracted text as one single document. We apply the same pre-processing and training steps for issue classifier as what we have done for commit classifier and code change classifier, which will produce a probability that the commit attached to the issues is a vulnerability fixing commit or not. Finally, from all three base classifiers, we obtain three probabilities that a commit is for vulnerability fixing or not, based on three sources of information: commit message, code change, and issue respectively. We employ a logistic regression classifier as our joint classifier to fuse these probabilities into the final prediction of HERMES. Next, I'm going to present our experimental results. There are two main questions that we want to answer specifically. First, how effective is HERMES for commits with explicit link? This question concerns with the effectiveness of the commit classifier when considered the true link between commit and issue. To answer these questions, we evaluate HERMES on the explicit link subset of our dataset. The second question is, how effective is HERMES on all commits when leveraging a commit issue link recovery technique? To answer these questions, we perform commit issue linking on all commits which don't have any explicit link to any issue, and then evaluate HERMES on the full dataset. In the first setting, HERMES improved over the baseline by 12.5%. The experimental result confirms our intuition that there is information in accurate link issues that is not captured from code change or commit message, and that is additional information improve the detection of vulnerability fixing commits. In the second settings, the improvement was smaller. This indicates that HERMES is sensitive to the quality of the link between commits and issues. When there is a significant amount of inaccurate links between commits and issues, the performance of HERMES is negatively affected. Despite the decline in the performance due to noise, HERMES still outperforms the baseline approach, which suggests that the use of commit issue link recovery can help if we limit the recovery of links to only the commits and issues that are most similar. So that's all for the content. Thank you for watching.